This video aims to provide a linear algebra perspective to an SVD-based audio watermarking technique. Let us first take a detailed look at the singular value decomposition or SVD. Singular value decomposition states that any complex valued m cross n matrix A can be decomposed as A equals U S V Hermitian, where the columns of U m cross m are eigenvectors of A Hermitian, the columns of V n cross n are eigenvectors of A Hermitian A. The R singular values on the diagonal of S m cross n are the square roots of the non-zero eigenvalues of both A Hermitian and A Hermitian A. U and V are unitary transformations. If A is a real valued matrix, then the decomposition can be represented as A is equal to U S V transpose with the following conditions. The SVD of A can be viewed as the transformations U S V transpose applied sequentially. We first look at the matrix multiplication form of this transformation, and for our initial discussion we assume that M is equal to N and A is full rank. We now have some essential remarks on each of the transformation matrices. The matrix A. It transforms any vector x in Rn to y in Rn. Further, the transformation A does not collapse the space Rn as it is full rank. Matrices U and V. The transformations U and V are unitary from Rn to Rn. The columns of U and V comprise orthonormal vectors. U and V transformations do not collapse the space as they comprise linearly independent columns. Also, they do not perform any shearing action as each of the columns are orthonormal. Thus, we conclude that U and V are rotations. The matrix S is a diagonal matrix comprising singular values which performs a scaling operation in Rn. The effect of such a transformation A can be analyzed for any given input vector. However, instead of analyzing the effect vector by vector, it is often easier to visualize a collection of vectors, say the set of vectors that form the faces of this cube. Let us now look at the effect of the transformation A on the cube. The SVD of A gives us a rotation V transpose about an axis, followed by a non-zero scaling S along the three eigendirections, and finally a rotation U about another axis. We can also observe that the dimensions of the transformed parallelepiped is the same as that of the input cube. Let us now look at the matrix form of the transformation when M is equal to N but A is not full rank. Here we can observe that the matrix S has zeros on the diagonal in addition to the off-diagonal zeros. This results in a scaling of 0 or collapse along one of the eigendirections. The matrix forms of any transformation A where M less than N or M greater than N would look like so. A sample transformation from Rm to Rm where M less than N can be visualized like this. So for any real value transformation A we can find a singular value decomposition like so. And for complex value transformation A, like so. One implementation of an SVD-based audio watermarking system works by embedding a watermark sequence in the STFT matrix of an audio signal. In short, the algorithm goes like this. Form the matrix A of F frames, each with M short-term Fourier transform coefficients. Decompose into U, D, V transpose. Consider W of the same dimensions, a pseudo-random noise matrix. Formulate WD, the watermark matrix, using the following steps. Decompose WD to obtain the diagonal matrix DW, and finally obtain the short-term Fourier transform matrix of the watermark signal. So when we compare the two transformations, we see that there is no perceptible difference. In summary, SVD-based audio watermarking adaptively embeds a watermark sequence in the singular values of the STFT matrix and ensures a high perceptual quality of the watermarked audio signal.